Right now, some of the smartest and wealthiest people on Earth are planning to send humans to Mars. Elon Musk, NASA, the European Space Agency, even Australia's own space program has Mars in its long term vision. And the public excitement is extraordinary. The idea of becoming a multiplanetary species, of humans setting foot on the red planet within our lifetime, is genuinely thrilling. But here is what the press releases and the promotional videos are not telling you. The physics of a Mars mission is absolutely brutal. Not difficult, not challenging, brutal. The radiation alone should give every prospective Mars astronaut pause. The bone density loss, the muscle atrophy, the psychological isolation, the rocket equation that makes the return journey almost incomprehensibly expensive. Richard Feynman, who served on the Rogers Commission investigating the Space Shuttle Challenger disaster, was famous for one thing above all else in his public life: telling the truth. Even when the truth was uncomfortable, even when powerful people did not want to hear it. Today, we apply Feynman's honesty to the Mars mission, not to kill the dream, but to understand it clearly. Because a dream built on honest physics is worth 10 times more than one built on wishful thinking. G'day and welcome back to Curious Physics AU, the channel where we follow the physics wherever it leads, even when it leads somewhere the marketing department would rather we did not go. I am Abdullah, and today we are doing a full physics audit of a crewed Mars mission. We are going to cover 6 physical challenges, each one serious, each one requiring honest assessment, each one shaped by the same laws of physics that govern everything else we have discussed on this channel. The journey time, the radiation environment, the effect of microgravity on the human body, the landing problem, the return journey, and the rocket equation, and the Martian environment itself. I want to be absolutely clear from the start. This video is not anti-Mars. The Mars mission is one of the most ambitious and inspiring endeavors in human history. Australian scientists and engineers are contributing to it right now. But Feynman always said, for a successful mission, reality must take precedence over public relations, for the hardware does not care about your feelings. He said that about the Challenger. It applies just as powerfully to Mars. Let us be honest. First, the journey itself. Mars and Earth orbit the Sun at different speeds. The minimum energy trajectory from Earth to Mars, called a Hohmann transfer orbit, takes approximately 6 to 9 months, depending on the relative positions of the planets. You cannot just point a rocket at Mars and go. Mars is not where it is now when you arrive. It has moved. You have to aim for where Mars will be when you get there, like leading a moving target. And the launch windows, the periods when the geometry is right for an efficient trajectory, occur only once every approximately 26 months. Miss the window, and you wait more than 2 years for the next one. So a crewed Mars mission involves 6 to 9 months of travel to Mars, a surface stay of approximately 14 to 18 months waiting for the next return window, and 6 to 9 months back. Total mission duration, approximately 2.5 to 3 years. 3 years in a spacecraft roughly the size of a Sydney apartment with the same crew. No fresh food resupply, no emergency evacuation, no possibility of rescue if something goes wrong. The longest continuous spaceflight record is held by Russian cosmonaut Valery Polyakov, 437 days on the Mir space station. A Mars mission would far exceed that record, and the space station had one enormous advantage over a Mars-bound spacecraft. It was still in Earth orbit. If something went catastrophically wrong and crew could be home within hours, on a Mars mission, there is no coming home early. Once you leave Earth's gravitational influence, you are committed. Physics commits you. The rocket equation commits you. You are going to Mars, and you are staying there until the window opens. Now, here is the physical challenge that worries space medicine experts most, and the one that receives the least attention in the breathless media coverage of Mars missions: cosmic radiation. On Earth, we are protected by 2 things: Earth's magnetic field, the magnetosphere, which deflects most charged particles from the Sun and from deep space, and Earth's atmosphere, which absorbs the remainder. In low Earth orbit, where the International Space Station lives, astronauts still receive significant radiation, about 150 to 300 millisieverts per year, compared to the average Australian on the ground receiving about 2 to 3 millisieverts per year. That is already 50 to 100 times the ground level dose. But low Earth orbit still has partial protection from Earth's magnetic field. Beyond Earth's magnetosphere, in deep space between Earth and Mars, there is essentially no protection. The radiation environment consists of two main components: galactic cosmic rays, high energy particles from outside our solar system, protons, helium nuclei, and heavier elements, accelerated to near light speed by distant supernova explosions. They penetrate almost any practical shielding. The heavier particles are particularly dangerous. They damage DNA, cause cancer, and degrade the central nervous system over time. Solar energetic particle events, massive bursts of radiation from solar flares and coronal mass ejections. These can deliver lethal doses in hours if caught without adequate shielding. NASA's radiation limit for career astronauts is approximately 600 millisieverts, a limit designed to keep lifetime cancer risk increased below 3%. The Mars Science Laboratory, the robotic mission that delivered the Curiosity rover, measured radiation during its 8-month journey to Mars. The total dose for the cruise phase alone was approximately 300 millisieverts. A round trip to Mars and back would expose crew to approximately 600 to 1200 millisieverts from the journey alone, before a single day on the Martian surface, that is at or beyond NASA's career limit from the journey alone. The Australian Radiation Protection and Nuclear Safety Agency, ARPANSA, sets Australia's radiation safety standards. The dose limits for Mars crew would far exceed anything currently considered acceptable for radiation workers on Earth. This is not a solvable problem with a slightly thicker spacecraft wall. Galactic cosmic rays are so energetic they pass through meters of metal. The only practical shields are large masses of water or polyethylene, or the planet Mars itself. The Martian surface, underground habitats, provides genuine protection, but the journey there and back remains the critical radiation window. This is the physics Mars mission planners lose sleep over, and it should be discussed honestly in every press release. Physics does not just threaten Mars astronauts from outside, it threatens them from within their own bodies. The human body evolved over millions of years under Earth's gravitational field. 1G, constant, unrelenting. Every system in your body, your bones, your muscles, your cardiovascular system, your vestibular system, your vision, is calibrated for 1G. Remove that gravitational load, as happens in the microgravity of deep space, and the body begins to adapt. Badly. Bone density loss. Without the mechanical load of gravity, bones lose mineral density at approximately 1 to 2% per month in critical load-bearing areas. After 6 months, astronauts have measurably weaker bones. After 18 months in microgravity, the cumulative loss is severe. Muscle atrophy, without gravity to work against, muscles, particularly in the legs and core, lose mass rapidly. Even with rigorous exercise regimes of 2 hours per day, the loss continues, just more slowly. Cardiovascular deconditioning. The heart does not need to work as hard in microgravity. It gets smaller and weaker. Blood pressure regulation changes. Astronauts returning to Earth often cannot stand without fainting initially. Visual impairment. A significant percentage of astronauts who spend extended periods in microgravity develop vision changes. Increased intracranial pressure flattens the eyeball and damages the optic nerve. The mechanism is still being studied. The effect is real and sometimes permanent. Now, here is the cruelest physics of the Mars mission. After 6 to 9 months of bone loss, muscle atrophy, and cardiovascular deconditioning, the crew arrives at Mars. Mars has gravity, about 38% of Earth's gravity. Not microgravity by action, but significant. The crew must immediately function in that gravity, conduct surface operations, handle emergencies, work physically demanding tasks, with bodies that have spent 6 to 9 months adapting to weightlessness. Every Mars mission plan includes aggressive exercise protocols during the journey, resistive exercise, aerobic conditioning, pharmacological bone density protection, and every honest assessment acknowledges these measures reduce the problem. They do not eliminate it. The bodies arriving on Mars will not be the bodies that left Earth. Physics makes sure of that. Getting to Mars is hard. Landing on Mars is terrifying. Mars has an atmosphere, but it is about 1% the density of Earth's, thin enough that it generates significant heating during entry, requiring heat shields, but too thin to slow a spacecraft sufficiently using atmosphere alone. Earth landings rely on the thick atmosphere. Parachutes work brilliantly here. On Mars, parachutes can be used but cannot do the job alone. The solution for robotic missions, the sky crane that lowered the Curiosity and Perseverance rovers, was extraordinarily complex. A hovering rocket platform that lowered the rover on cables before flying away to crash land at a safe distance. Extraordinary engineering, brilliant physics application, but the Curiosity rover weighs about 900 kilograms. A crude Mars habitat with life support supplies and return propellant would weigh tens of thousands of kilograms, potentially hundreds of thousands. Scaling the sky crane concept to those masses in Mars's thin atmosphere is one of the most significant unsolved engineering challenges in spaceflight today. The Australian Space Agency, established in 2018 and headquartered in Adelaide, is contributing to NASA's Mars missions through the Trailblazer program. Australian technology, Australian engineers, working on the precise problems of Mars surface operations. The landing problem is not hypothetical for Australian space researchers. It is an active engineering challenge being worked on right now, in part by Australian hands. We touched on the rocket equation in our interstellar travel video, but for Mars, it deserves specific attention, because it is the single most daunting constraint on the entire mission. The Tsiolkovsky rocket equation, derived in the late 1800s, describes the relationship between a rocket's mass, its exhaust velocity, and the change in velocity it can achieve. The brutal implication that every kilogram of propellant you need to carry to Mars requires more propellant to carry that propellant, which requires more propellant to carry that propellant. It is exponential, merciless. To land on Mars and launch back to Earth from the Martian surface, you need an enormous amount of propellant. Carrying that propellant from Earth adds exponentially to the mass, and therefore the cost and complexity of the entire mission. The proposed solution, and it is genuinely clever, is in situ resource utilization, ISRU, making propellant on Mars using Martian resources. Mars has carbon dioxide in its atmosphere, about 95%, and there is water ice at the Martian poles and subsurface. Using the Sabatier reaction, carbon dioxide plus hydrogen produces methane and water. Methane is an excellent rocket propellant. SpaceX's Starship uses methane-oxygen propulsion specifically with Mars ISRU in mind. The hydrogen can come from electrolysing Martian water ice. The oxygen comes from the same process, and from the Sabatier reaction byproducts. ISRU on Mars is theoretically sound. The chemistry works. NASA's MOXIE experiment on the Perseverance rover has already demonstrated oxygen production from Martian carbon dioxide, a genuine milestone. But scaling MOXIE, which produces about 10 grams of oxygen per hour, to the tons of propellant needed for a crewed return launch, is an engineering challenge of extraordinary magnitude. If the ISRU system fails, the crew cannot leave. If the ISRU system is not in place and working before the crew arrives, the crew cannot leave. The return journey depends entirely on a propellant production system operating reliably, autonomously, on another planet, for years before the crew even sets foot there. That is the physics of the return journey. It is not impossible, but it is genuinely, soberly, honestly daunting. Assuming the crew arrives safely, what does the Martian environment actually offer? The honest answer, very little comfort, extraordinary science. Temperature, Mars averages about minus 60 degrees Celsius at the surface. Summer near the equator can reach a pleasant minus 20. Nights plunge to minus 125. The thermal cycling alone would be engineering stress on any surface habitat. Atmosphere, 95% carbon dioxide, about 1% the pressure of Earth's atmosphere, completely unbreathable. Every surface excursion requires a full pressure suit. Every habitat must be pressurized and sealed against an atmosphere that would kill you in minutes. Dust storms. Mars experiences planet-wide dust storms that can last months. The 2018 storm lasted approximately 8 months and ended the Opportunity rover's mission. Solar panels become useless. Visibility drops to near zero. The 2018 storm would have been catastrophic for a crewed surface mission. Martian dust itself, potentially toxic, containing perchlorates, reactive chemical compounds, at concentrations that could cause thyroid problems with prolonged exposure. The dust is fine. it gets into everything. Managing dust contamination inside a habitat is an active research problem. And then there is the physics of isolation, not physical forces, but the physics of communication. The speed of light limits communication between Earth and Mars. At closest approach, in about 54 million kilometers, a signal takes about 3 minutes one way. At furthest separation by about 401 million kilometers, it takes about 22 minutes one way. A question from Mars. A minimum 6-minute wait for an answer. At worst, 44 minutes. No real-time conversation. No immediate medical advice. No psychological support call that feels natural. Every decision on Mars must be made by the crew, alone, with the understanding that Earth cannot help in real time. The physics of distance creates a psychological environment unlike anything humans have ever experienced. So, is the Mars mission a one-way trip? Physically, not necessarily. If the ISRU works, if the radiation exposure is managed, if the landing system scales, if the crew arrives healthy enough, if the dust storms cooperate, if nothing catastrophically fails, the physics does not make Mars impossible. It makes Mars hard, genuinely, soberly, profoundly hard. And here is the Feynman lesson I want you to take from this. When Feynman served on the Rogers Commission after Challenger, he famously demonstrated the O-ring failure by dunking a piece of rubber in a glass of ice water at a press conference, showing the assembled media exactly how the cold had made the O-ring brittle, simple, clear, undeniable. He was criticized for being too harsh, for undermining confidence in NASA, for being difficult. He was right. His final report concluded, for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. The Mars mission needs its Feynman voices, needs honest physicists and engineers saying, here is the radiation problem, here is the rocket equation problem, here is the landing problem, here is the ISRU problem. Not to stop the mission, but to ensure it succeeds. Australian scientists and engineers at the Australian Space Agency, at universities across the country, at CSIRO, are contributing to solving these exact problems. Australian developed technology is flying to Mars right now. The honest physics assessment of the Mars mission is not a warning to stay home. It is a map of the work that remains. And maps, as any good physicist knows, are more valuable than reassuring stories. So, let us bring it all together, Feynman style. The journey to Mars takes 6 to 9 months each way, with a mandatory 14 to 18-month surface stay waiting for the return window. Total mission, up to 3 years. Cosmic radiation during the journey, galactic cosmic rays and solar energetic particles will deliver doses at or beyond current career limits for astronauts. Shielding is limited. The physics is uncompromising. 6 to 9 months of microgravity causes significant bone loss, muscle atrophy, cardiovascular deconditioning, and potential permanent vision changes. Crews arrive at Mars physically diminished and must immediately operate in Martian gravity. Landing a crewed habitat on Mars using its thin atmosphere is an unsolved engineering challenge of enormous scale. The return journey requires in situ propellant production on Mars, using Martian carbon dioxide and water ice, demonstrated at small scale by MOXIE, unproven at mission-critical scale. The Martian surface offers toxic dust, extreme cold, unbreathable atmosphere, planet-wide dust storms, and communication delays of up to 44 minutes round trip. None of this makes Mars impossible. It makes Mars the hardest thing humans have ever attempted. And that, honestly, is what makes it extraordinary. If this video gave you a deeper and more honest appreciation of what a Mars mission actually involves, smash that subscribe button and join the Curious Physics AU family. New videos every week, built for Australian students and anyone who wants the real physics behind the headlines. Drop a comment below. Do you still want to go to Mars after all that? I genuinely want to know. Because the physics is brutal, but the dream is real, and honest dreams, built on honest physics, are the ones that actually get achieved. Share this with anyone excited about the Mars mission, not to discourage them, to make them understand it deeply enough to contribute to it. For the HSC and VCE students watching, the rocket equation, radiation physics, orbital mechanics, and space medicine all connect directly to your physics curriculum. This is your syllabus, made extraordinary. I will catch you in the next one.